So this next topic that we're going to begin here is one of the more applicable topics to real life, quote unquote, real life understanding, um, and it's called linear programming. Um, so let's just put that right up here, linear programming. So what this is, linear programming, it's a method for finding a minimum or maximum value of some quantity given a set of constraints. So what we have is, if we're given a set of constraints, let's say we're given x must be greater than or equal to 2, y must be greater than or equal to 3, y also must be less than or equal to 6, and then x plus y must be less than or equal to 10. Okay. So we're given this set of constraints, and the first thing that we should really start doing is thinking about what it looks like on a graph. So we can already determine some of these pretty quickly. X is greater than or equal to 2. Well, then we just go to x, 2, x equals 2, draw a line. Let's just make it a dotted line for right now. Okay. And, well, x is greater than or equal to. I don't want to get confusing, so we'll make it a solid line. X is greater than or equal to 2. Okay, and then y is greater than or equal to 3. So y value 3. Let's make a line there. Oops. We'll connect that. Okay. Y is less than or equal to 6. Okay, so 4, 5, 6. And then we'll make another line there. And then x plus y is less than or equal to 10. So this one we can actually solve for y and then graph. So this is going to have a y-intercept of 10, which is somewhere up here. And then it's going to have a slope of -1. So I know that this is going to intersect at a point of 4, 6. So I can go 1, 2, 3, 4, and then up to 6 and make a point. And then I can go down 1 and to the right 1, down 1 and to the right 1, down 1 and to the right 1, and then connect these points. Okay. So here, now we want to start looking at the inequality signs. X is greater than or equal to 2. That's all of this direction in the positive direction. Y is above 3. Y is below 6. And y is less than or below this line over here. So that actually becomes this area inside of this shape formed by these linear equations. Besides the x is greater than or equal to 2, which is not actually a function. But anyway, so the graph of this system, or this yellow portion that we've now shaded in, is our feasible region. So the quantity that we're trying to maximize or minimize using linear programming is usually represented with an objective function. So this objective function, we can write down here, objective function, this many times can be represented as maybe a cost or a profit, if you think about it in economics terms. So let's say that our objective function here is c is equal to 2x plus y. So for different values of c, we're going to have different objective functions that are all parallel to each other, but with different y-intercepts. So what we want to do is take these different values of c and different y-intercepts and use that to create different objective functions, different variations of the objective function to minimize and maximize our feasible region. So the way that we're going to minimize it is when we get an objective function that is closest to the origin, and the way that we can maximize it is one that is furthest away. So we know that at this vertex right here, a line that passes through that vertex would be a perfect place to minimize our feasible region with our objective function. So we want to figure out what objective function passes through that vertex. Well, that point there is 2, 3. That is 2, 3. So we know that our objective function is going to have a slope of -2. So that means that to go down 2 and to the right 1, we're going to have a point there. And if I were to go up 2 and to the left 1, we would have a point there. And then if I went to up 2 again and to the left 1, we'd have a point there. And there we are, we have our y-intercept, which is going to be 7. We have a scale of 1 here. 1, 2, 1, 2. So if our y-intercept is 7, that means our c value is going to be 7, and we can actually rewrite this equation as a minimum function. 7 equals 2x plus y. And if we were to draw a line through these points, that would be representative of that minimum linear function. Then our maximum function would be the line that would cross through this vertex here, because the line that's going to cross through that vertex is going to be parallel to the line that we just drew. So if I were to draw a line parallel to this other yellow linear equation, and then at this vertex, so we're always looking at the vertices, then that is going to maximize our feasible region and our objective function in the feasible region, the constraints that we're given. So how is that going to work? Well, again, we have a slope of -2, so if we were going to go up 2 and to the left 1, and then up 2 and to the left 1, and if we were going to continue to do that, we would eventually get to a y-intercept of 17 equals 2x plus y. And this is going to be the line that actually maximizes our function. Oops, I need to redraw that. So this line maximizes our function. Has a slope of -2, it satisfies our objective function, and it lives within the constraints. It has a point that lives within the constraints of our initial problem. So if we were to try to determine this a little bit more effectively, so this point here is going to be 7, 3. So at 7, 3, if I were to plug 7 into x and then 3 into y, that is going to give us a value of 14 plus 3, which is 17. And that's how I was able to determine that the y-intercept was going to be 17 so quickly. All I had to do was take the x value and the y value and plug them into the objective function and solve for c. So I knew that would be the function that would cross that vertex.